So I put together some slides, and I know that I can't capture all the aspects. So what I want to do is use the whiteboard. So whenever you guys have questions that is not captured in the slide, I'll just go to the whiteboard and use it. So when we first we kind of thinking about this all the data explosion that's happening when we were at VMware. Initially that time it was only vSphere, and we started seeing OpenStack in the horizon, and then we started seeing Docker containers also emerging. So our goal was always to kind of build a platform that is fairly broad enough to address various computing platforms around. So that was one of the biggest things that we had when we were at VMware, when we were leaving VMware. So Springpath Data Platform is a singular data platform that is trying to meet the data needs of all these compute platforms. Be it VMware, be it OpenStack, KVM, be it OpenStack Docker, or even a bare metal to a large extent. So we wanted to build a platform that can broadly be applicable to varying workloads. And it's going to be 100% software. We always wanted to build something that's purely software based. We wanted to build something that can scale, because customers are not, you don't want customer to be locked into doing POCs by paying huge upfront costs. We know that customers always want to have an ability to go gradually by adding elements to it, and that the cost of adding element should come with a reasonable limit, not in hundreds of thousands of dollars, but rather in tens of thousands of dollars, even if they wanted to. So that was one of the things that we thought about. And the other aspect is really about enterprise grade, and I'll get into data integrity, data availability in the next few set of slides. What we wanted to do was, a lot of people, when they want to introduce a disruption, either go to Docker or into the Hadoop or other environments, one thing they fundamentally miss is that in the line of business, it doesn't come across as a big issue, but as soon as it goes into the mainstream IT operations issue, compliance, DR, backup, and data integrity, data resiliency, snapshot, all this becomes an issue for them. And then, so some of these environments, especially around test and dev, I don't know if you guys notice in Docker and other environments, you will see that, in Hadoop also you will see that, and that's one of the areas that MapRS, for example, is focused on. So we want to always build a platform that gives us the richness of enterprise grade, good data reliability, data availability, and integrity guarantees. As you take the IT infrastructure from mainstream vSphere environment all the way up to OpenStack and Docker and other environments. The other aspect is, every server administrator is used to managing a form of servers using a particular management portal, right? So we wanted to make sure that his experience, his life in terms of dealing with the infrastructure has to be made very simple. So that's why we are focused heavily on, even though we are introducing a piece of software that is actually delivering a storage-like functionality, the management of that, we want to make it extremely simple by integrating into the existing management offerings that are compute to the compute platform management constructs. So essentially, we wanted to deliver a data management storage software on a commodity server without compromising performance and features. So before going into the architecture, at least I want to state few design goals when we started this company. First thing we wanted to do was, obviously every single scale-out system wanted to scale performance and capacity and the performance linearly, right? The other aspect, when we started looking at how is the data center layer, blades and 1U and 2U and 4U, how all these things are evolving. See, we wanted to keep something in mind that we wanted to enable both the legacy as well as a near one, and what that means is that I'll go into one of the details about how we scale caching layer and the persistent layer independently, but we always wanted to bring that into the equation as the environment starts morphing from mainstream to non-mainstream environment. And the other
Alec, it's interesting that you would say that you want to be able to scale the caching tier and the persistent tier differently. Is the caching non-persistent?
No, caching is still persistent. What I mean, I'll tell you a very specific example in this particular case. Imagine you have a rack of servers, right? And some are blades. Let's say you bought into blade because you like the blade management stack for the blade, right? Like, give you a very simple example of UCS. People like UCSM, UCS Director. They bought into this. So they have the existing investment. Let's say that they wanted to try this new class of offerings, and then they wanted to buy, let's say they are willing to do 1 use and 2 use and 4 use, they bought few of them and they racked it up. Now you can actually really create a cluster amongst all this. The existing blades, you have now 2 choices. You don't have to put hard disk on all of them. You can actually use them as a compute only and mount the data store that's coming from the remaining 1 use and 2 use. That's one option. The second option is blades have at least two drives, right? So you can put SSDs there. So now you can actually really create a distributed storage system where caching spreads across your entire the rack, persistence spreads across only a few. The rack units you added 1 use or 2 use, but the whole cluster is cohesively managed as one entity. You get performance through the caching tier, the capacity from the persistent tier, yet you did not lose any data management capabilities.
But the caching tier and the persistent tier don't necessarily have to be on the same server?
Exactly.
Yes.
Precisely.
And the caching is persistent.
Yeah.
And the caching is persistent.
And
that's also good.
If you let me draw, I mean, pictorially it looks something like this. If you took a rack here, so you have a bunch of blades here. I mean, I'm drawing a chassis here. Sorry. And then let's say you put in a bunch of rack elements here. Let's say you build a 2U rack with both SSDs and HDDs attached to it. Right now what you have done is that you can now let's say you created a cluster out of this, right? So a Springpath cluster, you can now mount this data store. You get the complete scale out. That's one way of doing it. The other way of doing it is also now let's say you only put SSDs here, right? And this also became a part of this cluster, right? Now if you look at logical view of this, your data store spans across this entire rack because it's exported to all of them. Now the caching tier spreads across only the nodes that have SSD. So you have nodes SSDs here. You have some blades.
And you support like PCIe flash as well as SSDs?
Yeah,
yes.
we support both of them.
It is independent of the medium, so it can be PCI flash or the SSDs.
Yeah. Now you can even
do you access the disk controllers via IO direct path, or you're going through
exactly. So I'll go into that one. Its short answer is yes. We in the VMware environment. Let me just quickly answer this. I may or may not get to it. So in the VMware environment, let's say you have a single node. Just look at single node. In the single node, you have hypervisor installed. Into it, we actually install a Springpath controller VM. The Springpath controller VM is given some amount of memory, some amount of CPU, and then we take the HBA into VM direct path board. Okay, so we see the entire sets of devices. That's what we do in VMware environment. In Hyper, we do the same thing, more or less, right? Instead of VM direct
they have a different name for it. Yeah.
Yes.
And then third, in the case of what we have done pretty clever on OpenStack and Docker and bare metal Linux is that we've written our own file system from ground up. It all runs in user space. We have put the whole code in Docker container. So we run the entire stack in Docker container. You may ask why. So when I started thinking about OpenStack, like there is about 5 different variants if you look at it, right? You have a OpenStack from Red Hat, OpenStack from Piston, OpenStack from Nebula, OpenStack from Ubuntu, and then Mirantis. And each one of them use their own distros. And fundamentally we don't have any kernel dependency, right? But yet there are environments in which they don't want you to install certain things, and the upstart is different in Ubuntu. It is a supervisor D in others. So we want to completely isolate ourselves from any of this environment. So what we did, we ran the entire stack. Like it looks like Ubuntu 12.04. It runs actually entirely in a Docker container. So now you have very good image management, right? You deploy a Docker image on all of them, bring up the stack, and it's almost like as good as you're working on bare metal, because Docker is just like user level process, right? So it's a fantastic one. Now we form a cluster and we expose it. It's as good as like natively working. You get the benefit of image management. Now Docker allows you the registry server. Now we can
and you pay a tiny bit of
latest images,
tiny bit of latency in accessing the media,
which is another beautiful thing. You get a very good latency because as good as a bare metal. The biggest benefit, more than performance, is the image management, right? And you think about it, right? We can even do a very good rolling upgrades. So it's like you have one image here, another image in another container. You can bring it down. It's like almost like the CoreOS like active. How they manage the partitions. You can go between, roll back and roll over, and those type of things. Those are like a lot of benefits you get with the being able to run in Docker image. And most importantly, we may be going to an environment where may not be a virtualized environment, there may not be a KVM. So how will you work in this environment? So really, Docker kind of gives us the ability to run across all this. The other aspect, obviously, we will go into the details about Flash. We use Flash for performance. Then by that what we mean by is mostly for caching, and then we use hard disk, any slower media. It doesn't have to be hard disk. We use a slower media for persistence or capacity. So I may use the term interchangeably, capacity and persistent. That doesn't mean the caching layer is not persistent. So I'll come to it. So and then we wanted to actually completely avoid bin packing. Where, what I mean by bin packing, we wanted to eke out capacity anywhere within the cluster, be it a same node or be it in another node in a cluster, be it a gigabyte worth of data. We want to be able to achieve this high level of pooling, both in the capacity tier as well as in the persistence tier. And then we want to maximize the space usage. Obviously, you will see in the next sets of slides that we heavily talk about replicating data across the servers for high availability. And obviously, by that, you are losing the usable capacity. So we wanted to gain the capacity that we lost during replication by using inline compression and dedupe. And then we wanted to build a highly efficient snapshot capability. So we not only want to make a snapshot operations very fast, we want to make sure that the whole CRUD thing works extremely fast, scale extremely good. So that's what we wanted to build, because a lot of environments, fast cloning, number of clones, test and dev. We want to give even the ability as we start going to test and dev in the future, let's say Docker and other environment, you are going to see a huge explosion in terms of the number of copies you'll see. You imagine if you gave each developer a ability to do snapshot schedule and weekly, nightly, daily, you don't have to worry about data being lost.
So what are the limits on system-wide and per object numbers of snapshots?
Yeah, so we essentially the snapshot ID that we are using, it's a 64-bit. It's essentially 2 raised to 64 per object.
So the granularity
probably enough.
Theoretically, it is big. We have tested. I think our first customer probably use heavily nightly type of. So they probably use a nightly snapshots for the last 1 year or so. So.
And what are your limits as far as compression and deduplication, since it's all handled inline? Metadata maximums, where is that stored? Does that scale as you grow the cluster or as it shrinks or whatever the case is?
Yeah, so the way we do compression and dedupe, I'll go even more deeper. Short answer is basically it is compression because we wrote our own log structured file system. So when you write your own log structured file system, obviously compression is a variable size block. So when you write a log structured file system, that is one thing you get for free. As we purge the data to either to the SSD or to the hard disk, all the data is compressible as we append to the log structure.
Well, so there's a system memory. The log is in system memory.
No. So
okay, because you just said purge to SSD.
Yeah. What I mean by purge.
So you're purging from one piece of flash to another.
Writes, it is written to the SSD, but it can be compressed there.
Yeah.
Yes.
It was about persistence. You answered the question.
Sorry about usage of thanks for correcting. So. I'll go into the writes. Essentially, whatever the writes, any writes that we service, it's always going to go to SSD. It's persistent always. And I'll also go through how we acknowledge and all that when we acknowledge. But as we write to either to SSD or when we destage the data that we wrote to the write log, which is SSD, to the persistent media, which is what we, when I say persistent, that's why I use a term.
You're using persistent as to mean end destination, not will survive a power failure.
Exactly. Sorry, so I couldn't come up with I used the word capacity, but then if you put lower speed SSDs, like do people call it SSD?
Yeah. So it's permanent home.
It's a permanent home. Yeah.
Every write which is acknowledged is persisted to the persistent medium. It can the SSD is a persistent medium there.
Right,
so
and
it survives the power failure.
And on multiple nodes.
On multiple. We'll go into the details.
Yeah. So I have a very illustrated examples of this. We'll go deeper, and also even in Snapshot, if you guys want, I can go deeper. Like I can go into whiteboard. The other aspect is really want to go extremely fast cloning. In a demo, you'll see that we can do clone customization and all that. we wanted to really, this is the other point I was telling you, we really wanted to support a wider variety of compute platforms, VMware, KVM, Hyper-V, and containers. And last point is really we wanted to empower the server admins. He's already trained in certain management portals. It will be hard for him to learn yet another management pane. So that's a philosophy that guided us to do what we did today. And we will have a demo and I'll talk through a little bit about it. So before even going to the architecture, I just want to give you a very quick deployment. I think you guys talked about, hey, how does a single host look like, right? So the deployment scenario is we need a minimum of 3 node, right? So minimum of 3 node, you start as we have a minimum of 3 node, and our controller software is installed each one of the hosts. As I mentioned, the controller piece of software on a VMware environment is a VM, Hyper-V it's a VM, in Docker, in OpenStack and KVM and Docker, all this environment, even a bare metal, it is just a Docker container. We start as a few, so 3 servers. Obviously, we form a cluster. We create what we call a data store, which looks and feels like, because of vSphere as well as in the OpenStack, it looks and feels like an NFS to the ESX host. It gets mounted automatically as the cluster gets added, and when you want to add a node, let's say a node gets added, a node is able to publish its resources, be it SSD or a hard disk. It gets automatically added to the system, to the cluster. And if the node is advertising SSDs, it becomes automatically be a part of the caching tier. If the node also exposes hard disk, it will also become a part of the HDDs. Obviously, if the node doesn't have hard disk or SSD, it can only be a compute only node, right? And while we add this, we are able to distribute data both at the cache tier level because when you add a node, obviously you have imbalance in the system. So you want to be able to distribute data both at the caching tier as well as in the capacity tier. We do this automatically. And obviously, this also allows you to retire nodes, either for the maintenance reason or you want to completely, because it's a faulty node, what have you. So we allow that. And system, as soon as you take this node out, system automatically rebalances. Sorry. Right?
Can I pre-schedule the eviction?
Can I
want to put the new node. I want to put the new nodes in during the day, but I want the data movement to start at 4 o'clock in the morning.
Yeah, right now we don't have it. That is the thing. We can probably definitely.
The data rebalancing can be configured based on the time of the day that we are planning to add. That.
Yeah, rebalancing you can configure. You wanted to make sure that I want to schedule.
5 years from now, I've got 10 nodes of 2 generations. I'm adding the new 3rd generation. I want to evict the oldest ones.
Yeah.
Mm-hmm. But I want to do the work of racking and stacking and adding to the new nodes to the cluster at 2 o'clock in the afternoon, because I don't like working nights and weekends.
Okay.
But I don't want the data movement to happen at 2 o'clock in the afternoon because it's going to present load.
Got it. Now I get it. Okay.
Yeah. And so I want to say evict these nodes at 4 a.m. tonight.
Yeah. Not exactly the time level we have it, but we have hooks in place already.
Okay.
Very good question. So this is just summarize the value prop, right? I mean, we allow you to add compute node. You can start adding compute nodes, and you get all the scale out benefits of the underlying data stores. You can actually start scaling the caching tier by adding a node into the cluster with SSD only. And optionally, you can add nodes with hard disk as well. It will become part of the capacity.
You have a node that has mixed SSD and HDD?
Yeah.
Yes,
so you can. So imagine, I mean, if you had a pure, I mean, for lack of better wording, I use this pure hyper-converged, where you have a node with everything. That is going to act as a compute node. It has an SSD. It becomes a caching node also. It also have a bunch of hard disks. It becomes a persistent node. And when you add a blade to the cluster, and the blade, if it doesn't have any SSD or HDD, it becomes a compute only node. Let's say you pop in one of the SSDs in one of that, and you had a controller VM software there, it becomes part of the caching tier automatically. So we'll distribute only the caching virtual nodes, which I'll talk through, to those elements.
So if you have only one SSD, it's a read-only cache, or you need at least 2 SSDs?
We need, that's a very good question. We'll get into this. We need a minimum of 3 SSDs in the entire cluster to be fully operational.
In the entire cluster, though, not
the entire
per
cluster,
node. Okay.
exactly.
Yeah.
We also,
one
exactly.
server?
But you are right. It is for the entire cluster, right? And then we also operate on 2, what we call is a degraded mode. When we go to 1, we go into what we call is a read-only mode, because obviously we don't want to take a write on this and then go down and then we have data loss. But we do have some customers who wanted to override even that. So we have given even that option, because that is almost like, hey, give me a gun, I want to shoot my food.
But in a VDI environment, that data
That
just
is
might
good.
not be valuable.
That is true. The key point there is like the replication factor you can configure, and the availability of your data depends on what is your replication factor.
Okay, but the defaults are on the safe side.
Yeah, on the safe side.
Defaults on the safe side. So in our 1.0 product, we did 3 copy. In the 1.1, which is going in a couple of weeks, you can do 3 copy and 2 copy.
Essentially double disk failures and double server failures.
Right.
So when you add a node, can you have, so we're talking physical server, can you have a portion of that dedicated to like VMware activity and a portion dedicated to Springpath as a data? So can I have, like, let's say it's got 6 disks and 2 SSDs. Can I take half the disk and 1 SSD and define it to the VMware?
So
other half not?
Yeah, so let me run through some deployment scenario. This may be, and I can explain this. So at the minimum, we need to boot ESXi, right? You need to boot ESXi, you need to have a var, core, the other partitions as well.
Yeah, that's what the thumb drive's for.
Correct. So what we do is that we use SD flash predominantly, the SD card as a boot mechanism, and then our controller VM only boots with launches itself through the partition that you set up for SD flash, but it takes the entire HBA in VM direct path. Once you take an entire HBA in VM direct path, now the access to ESXi is gone, because the way VM direct path works is that it's at the PCIe level. All the resources attached to it cannot be seen to VM kernel. The controller is taken over by.
So we'd need a second disk controller to split that.
Exactly.
It's not EMIS.
Because they physically own the disk controller.
To support RAID configuration, you need like 2 controllers, one for the ESXi and one for our controller VM, if you want the mixed configuration.
Yeah, the only there are some servers, I can tell you, I think R630 or 630 or 730. There are C240s, Cisco.
But they
all have what they call as a back drives. HP also has a DL380 series. You have back drives, and the back drives are attached to typically HCA port. That one actually you can assign it to the VMware vSphere kernels. Please.
Can I leverage my existing storage over network instead of the hard disk drives? So if I have an FC controller in my
I see.
Yeah.
So, I mean, you are saying essentially I have a network attached storage, then can your file system be mounted on top of that? I mean, in theory you can do it. I mean, we can take the control of the devices and then you can format the file system, but you lose the value proposition of.
So, yes. Short answer is yes. Technically, we allow that because of VM direct path we can see the entire line.
But the real answer is you're not going to support it.
We're not going to support it. Value prop is adding up all the resources of the different servers and aggregating and provide what the network attached vendors have done.
Obviously, networking, the storage array vendors would love for us to support it, but we are trying to take them to a different path.
Yeah, well, I mean,
I would say
that's what you want. Go see Satcham.
So
it could be some of each.
Yeah. I think the biggest gain you get with the VM direct path, in my opinion, I mean, we contemplated heavily. The biggest gain you get is the slot management. You get a fantastic slot management benefits when you do VM direct path because firmware directly provides that to you. The second aspect is really lot of SmartMon tools you can run inside it. You can figure out things like how many sector remapping happened on hard disk, where am I with the wear level indicator on the SSD. You get all those cool stuff that in the future you can actually start using this information, do things like what you've been talking about, scheduling things, right? You talk to scheduling in the context of retiring node. You can now start thinking about, hey, proactively at 70-80% we can actually start sending through ASAP information that this SSD is going down for this guy.
Have you gone far enough to build the smart library? The SSDs will all tell you via smart how much they've worn out. Unfortunately, they all tell you differently via smart how much they've worn out. Have you cross-referenced the HCL so that your ET phone home data includes?
Honest answer is we haven't cross-referenced anything. We spoke to I don't know whether I can say the name, but we spoke to one company which makes lots of SATA SSD, nice, very high performance SSDs. They did say that their firmware that reports through the SmartMon is pretty accurate. Okay. Now there are lots coming in now with competing with a very similar.
Yeah, I mean it's there in all of them, but which smart counter it is isn't standard, and so it would be nice if you went and said, here's our HCL, and here are the 8 SSDs we support, and we put in the logic for those 8 to pull that and once a month send ET phone home data so that I know what the wear status of my SSDs is all the time.
Yeah, it's very good. I mean, that's where we want to go. I mean, the more smart information we collect, it helps us to do a lot of things. Like, for example, if I see a lot of sector remapping happening on a hard disk, I can now proactively start doing rebuilds on other things. I don't need to be waiting until the disk tells me I am dead, right? So there are some cool stuff you can do with that. So that was the biggest gain for us, right?
So one of the things, it seems like most of this is fairly abstracted. At what point can the data providers, can we mix and match in one cluster like VMware with Hyper-V or a bare metal solution to provide a distributed file system across providers?
Fantastic. That was a demo that I was trying to put together. I don't know whether we'll ever get to it, but we'll do. The short answer is yes. So
I forgot
we built
you guys
a demo.
did bare metal.
So I built a cluster. I think I was drawing to somebody. I was explaining during the happy hour yesterday with one of you. So we built a cluster where we had, for lack of better, I built a 4-node cluster, OpenStack running on all of them. We had on 3 nodes, we have a KVM as a hypervisor. On 1 node, we have Docker as an hypervisor, which we will see in today's demo. Our Springpath controller software is running as a Docker container in each one of them. So that data store is now. So you have a VMs running on top of KVM. You have a Docker containers running on top of the same data store. Now we actually expose this data store to another compute element, which is running all vSphere ESX 5.5 and running VMs on top of it.
So vSphere on Docker.
Sorry?
So vSphere on Docker.
Yeah.
Was it vSphere on Docker, or was it multiple things running on the same?
Because Docker's providing the storage.
Pretty interesting. And then NFS is exposed to all the Linux.
But I mean, think about it at scale. You could have 4 bare metal machines running Springpath on Docker. Now that's $48,000 for 3 years, but that's the entire storage cost, as opposed to vSAN, where if I got 20 compute nodes, I got to pay for vSAN on 20 compute nodes.
Yeah.
And I'm not buying even the VMware licenses for those 4 nodes. So the costs balance out that way really well.
Exactly.
You nailed it. This was the biggest use case we actually hear from one of our customers, that every time I add another one of those hypervisors IP, license fee there, I don't want to keep paying, because I may not have that much of storage requirement in the first place, but I may have a compute requirement for all of them. Even if I do have it, I'm going to put 4 RU or 2 RUs. 2 RUs carry 22 disks. And if you put 4 terabyte drives there, I mean, you have a single node giving you 88 terabyte of space. And if you have a 4-node cluster, that's a lot of storage. Now you can actually expose all the storage without paying a license to others. But if you have locked into, already bought those licenses to run on supporting blades, but you haven't paid additional one, because each additional one is going to cost you anywhere from $10,000 to $20,000, right? So that's you can cut the cost. Very good point.
In your architectural description, you have Springpath controllers. Is there a Springpath client as well as server, or?
So I'll go into the detail, but the short answer is there is a concept of a redirector. There's a piece redirector that gives you this ability to stripe I/O requests across the cluster.
You're going to go into details, right?
Yeah, we'll go into the detail.
I'll wait.
Yeah. So simple answer. If you want to look at So let me not really. So if you look at the Springpath data platform, there is essentially 3 category of components, right? The top one is what we've been calling is a data access layer, which is actually providing a way to get to Springpath data platform through the compute platform, be it a Docker, a Hyper-V, or OpenStack. And then on the other side, which is the monitoring and orchestration, we support auto support functionalities, REST APIs, and those type of things. It allows you to do more like DevOps style, as well as the SaaS-based monitoring, metering, and those capabilities, double ticketing capabilities. The core, what we've been calling, is a halo, which stands for hardware agnostic log structured object. I mean, this is something that we wrote from ground up, and we wrote the whole thing in POSIX user space code. Everything is user space code. Everything is written in POSIX. It's all capable of running in container with no dependency from any of the Linux file systems. So let me kind of walk through each one of the layer, and let me start with the data access layer. Okay, in the data access layer, what do we do for VMware? In the case of VMware, we actually make it look like an NFS v3.
Just for context, we put it on a slide up here so that you know what he's talking about. The data access layer is that first thing. That slide refers to that first arrow, red arrow. Arrows will keep moving down as he keeps talking. So.
Wow, that's high tech.
Yeah. So it's a multi-layered cake, so I'm trying to walk through one at a time. On the ESXi, imagine you have a data store exported by a bunch of servers that has spindles and SSDs attached to it. That data store gets mounted across the ESXi host. We make it look like an NFS v3 to the ESX host, and we support VIA and vVol there. In the case of OpenStack, we again make it look like a NFS, and then we have a Cinder plugin there to provide all the volume level snapshot and instance snapshot on all those capabilities. In the case of Docker as a hypervisor, we can actually expose that to the host as to the container, the user containers as a volume, or we can also expose this as a block device.
So the choice of the NFS on the ESX was very specific because we wanted to get the functionalities offloaded to our backend as much as possible. If you expose a block layer, then you have the host-based file system which will abstract our capabilities.
Well, certainly in vSphere 5, it gives you a lot more information.
Correct.
In 6 with vVols.
Yeah, vVols, it will be even more transparent.
Yeah. And then on the Hyper-V side, obviously, Hyper-V is not a big fan of supporting NFS, so we actually, in that environment, we will be supporting SMB3O. So the front end to the Hyper-V will look like SMB3O, but back end is a protocol that we will control. Same as what we did for ESXi. It looks like NFS v3, but behind the cover, we have our own NFS like RPC across the entire farm of servers. So the next aspect is all about data distribution, right? So that is the second layer. After you do access, we exported this, and the next layer is data distribution. Before going to data distribution, I just wanted to give a little bit of context. What is the problem we are trying to solve with the data distribution? So if you look at a cluster with the servers and the SSD attached to it, you really have a distributed caching spread across the entire cluster. We wanted to leverage the caching capabilities available to us across the entire cluster. That was the biggest thing. So let me illustrate with this very simple example. If you have 3 VMs or 3 containers running on a host, and if all of them are forwarded to the local controller, then you have a hotspot. Essentially, you could have a hotspot. What we want to do was, you have a resources distributed across the entire cluster. Why not leverage everything? So what we are able to do is that we are able to stripe the I/O requests coming from different VMs, even if they are originating from the same host, across the entire cluster. So this is what we've been using as a data striping.
So there's no data locality for the cache or for the persistent layer.
Correct. So this layer, the data distribution layer that I'm talking, is at the cache layer right now, and then I'll go into the details of how even at the persistent layer we do data striping. When we destage the data from the caching tier to persistent tier, we stripe the request across the entire cluster by leveraging any of the data we nodes, and I'll talk in terms of what's the granularity there.
But this data is already deduplicated in the cache, right?
On the right side, so that is the next slide. I'll talk about it if you wait.
Well, no, I just realized that with deduplication, locality is ridiculous because you want locality to where the workload is, but if the same block appears on workloads on all your servers, then locality doesn't make any sense at all.
Randomize itself.
I think biggest benefit
having the bigger cache will give you more bang for the buck than having the locality.
Exactly. That is one aspect. The other aspect is like you were mentioning about locality is very good spot on, is that as the VM starts moving within a cluster because of DRS policy.
Yeah, we heard that this morning. We buy it.
Okay. So, very good. Okay.
So is there any requirement like all the even distribution of cache, like all the nodes in a cluster should have same amount of cache or something?
No. I will. The next slide is exactly that. I will go as deep. If I did not answer you, ask me again.
Okay.
And I will. Sorry about that. I just
try
thought.
to understand. Did you say on the VMware environment you support NFS?
Yes.
Yes.
It looks
So
like
then you could effectively be an NFS server for any solution.
Yeah, that is technically right, though that's not the market. I'll tell you why.
You don't support
Market.
the full POSIX locking.
Exactly.
You got it.
Because of
Yeah.
the distributed
You nailed it.
nature,
Exactly.
we don't have the
So-
distributed
Right.
locking.
So like Coho Data, it's an NFS store
for
for
VMware.
VMs.
VMs, yes.
Exactly. So we say you nailed it. So we don't support multi-writer, concurrent writer because we don't give you any NLM, the NFS lock manager to you.
As you move to Hyper-V and you support SMB, the same sort of thing. I mean, you could potentially support SMB for any Windows user.
Yeah, SMB is you're
little bit
right.
different game,
SMB is
right?
much richer because of all the opportunistic locking and all that. It gives you more primitives to play with. NFS v3 didn't. That means you need to build NLM outside of this and then ship it to it. I mean, obviously, I don't think it's a technical decision. It's more of a business decision. Where do we want to focus as a startup? So we kind of focus on it.
SMB makes a lot more sense, especially for VDI, because you must have a good file store for VDI to hold the persona data.
Yeah.
Correct.
And with most hyper-converged solutions, they solved the VM part of VDI, but you still need a NetApp filer for all the persona data and home directories to live on.
Very, very good point.
Very good point.
Very
Yes.
good point.
Yeah. That's where the coexistence with the
Yeah.
bare metal also comes into the picture.
Well, that's a very good point. I wasn't thinking that. Yeah. So effectively leverage cache across all the SSDs in the cluster. I mean, you said I don't need to preach on this, right? So on the data, so let me go to the data virtualization. This is where I'll get into the details. I wanted to say we not only do striping across VMs, actually we do striping within the VM also. Let me explain what that means. Is imagine, I put two VMDKs here, let's talk only in terms of one VMDK. We look at the VMDK, we look at this logical address space, LBN space. We chop them into multiple chunks, what we call logically, right? We call them stripe units, right? So
How big is a stripe unit?
so it's a configurable right now. So right now we kept each chunk set with 256 MB. It's configurable, and also the number of stripe units is also configurable. That is about 8 now.
Okay.
So it's almost, you want to think about every 2 gig it rotates, right? You modulo, and then the next 2 gig and so on and so forth. The first 256 meg goes to the stripe unit 1, and the 2 gig plus the 256 meg goes also to the first stripe unit because of modulo. And we chunk them, and now the job is how to send the stripe into a caching tier, right? So with that, let me introduce you a few terminologies. Our goal is to take a stripe and route it to one of the cache vnodes. So what is the cache vnode here? So we have come up with this unique way of grouping SSDs and how we spread the cache vnode. So every node, when it comes up, it exposes, let's say, an SSD. So the nodes that are exposing SSDs are actually been noticed by our cluster resource manager. Now your cluster resource manager really looks at this as a distributed cache. Then it takes a bunch of cache vnode. Think of this to be a distributed hash, right? It takes the distributed hash and evenly distributes across the entire cluster. So for example, imagine a hash space of, I don't know, like
So it's content addressable storage, where each storage device is responsible for some section of the hash space.
yeah.
Correct. I mean, what Malik meant is like there's a notion of a vnode, which is a logical entity which gets distributed on different physical entities like the p nodes, and this logical entity allows us to address the data by that vnode and to the p node, which is managed by the cluster resource manager.
Okay, and I'm getting ahead. Go.
Okay.
No, you can ask.
Go ahead.
So
I know there's a slide, and when it's up, I'll ask the
So there's
question.
no requirement for a vNode to have the same amount of SSD storage.
No.
Right? So
No.
you can distribute a portion of the hash space to it and a larger portion to another one.
Another
exactly,
node, yes.
that's where I'm going.
That's where
so
we-
the primary reason for, I mean, you can use IP address. Why not use IP address, right? So the primary reason is that we want to be able to decouple the ability to serve the data from the location where you are serving it from. That's a fundamental. This is basically an abstraction, right? You build a virtual node, and this is a floating number. It's a floating object in some sense. You can move around them within the cluster. If, for example,
And the
when you
caching data is actually replicated as well for redundancy purposes.
exactly.
Correct.
Yeah.
Yes.
So I have a life cycle of a write. I'll go through the next slide. So we support mirroring and all that stuff. So the point I was trying to make here is that when
How do you know when a data is in the cache versus not in the cache on a read?
so I'll come
There's
to
a life cycle
actually,
of the read also. We'll go into the details of that.
So I'll explain here. So when you add a node here, obviously, we wanted to distribute cache across the entire cluster. So it is quite possible that you may have data that was sitting here that got moved here during the rebalance. Today, we don't move the contents from this cache to that node effectively, but we are looking at, and the cache on the other side will be cold, but we are looking at a way to kind of move the data as well, be addressable from the old tier as well. So the other aspect is by your ability of decoupling virtual node from the physical SSD, it gives you ability to move the virtual node across the servers now, right? It also allows you to, if you do a QoS-based, load-based rebalance as well in the future. For example, if you see hotspots, you will be able to break the hotspots by splitting them across the servers. That is another ability you get with this. So now the stripe gets routed to one of this cache V node. The act of that getting routed is done through the way we do that is some kind of mapping service. A trivial implementation of mapping service that we implemented is a consistent hashing.
It's easy. It works.
It easy work. What we are looking at, like I was talking a little bit about this hotspots on these two things. That time, what we have to do is basically load based, right? So even though two objects map to the same hash space, if you want to split them, then we need to look into other mapping services where we have a cluster resource manager. We can actually do a lookup on this.
And eventually you want to see it's hot enough, and I'll cache two copies in two places and distribute the reads across them. And
exactly.
Yeah, but
so that
crawl before you walk. It's fine.
Yes, exactly. So the key is like that particular unit of cache V node can be moved if it is seen as a hotspot.
Right, and so you can move it to a server that's less busy so it can provide service better, and then later you can duplicate it, and all sorts of games you can play.
And when you do that, of course, you're going to have to redefine the mapping from the hash space to the actual vnodes.
Exactly. That is precisely what, very good point. So right now we do consistent. With the consistent hashing, you can't change it, right? With the mapping services, now we can change it. That's where we're going.
Now, is the intention that we, as the owner of the application, the owner of the system, have to go through and manually rebalance things based upon hotspots, or will the system detect that, and as we add on, decrease, or otherwise spread the load to properly balance it as necessary?
So it's the latter. It will. The system recognizes how the hotspots are and then redistributes the data and the performance and the capacity to
Our rebalance is automatic too.
If it can, at least,
Yes.
If you're running the system at 100% utilization,
then
yes,
you don't want to burn the resources for the moment itself.
So the other one is, sorry, I went back. So let me walk through, I think you asked about writes and you asked about mirroring. Let me walk through a life cycle of a write operation, right? Imagine one of the stripes, VM was operating on a particular VMDK offset, right? And it was doing a write on this, and that write stripe, maps into, let's say, stripe unit, and that got mapped to one of the cache V nodes. Okay, even though I drew only one cache V node, assume that there are a collection of cache V nodes there. For a easier example, I picked this. And when the cache, the write happens on a cache V node, we have a concept called write log, which is analogous to a NVRAM equivalent, right? So essentially, all the incoming writes, we operate in servers. This is NVRAM in servers, so we essentially use SSD, and a portion of SSD is marked as a write log.
Can I specify that? Can I have a Intel P3700 and use that as the write log and something less expensive?
Correct.
You can do that, and right now we have not exposed the knob of how big the size is to the customers. It is configurable, tunable, but it will come up with a default value of 2. We have 2 partitions, and I'll go into the write log partitions and how it operates. Essentially, we take an SSD, a portion of SSD, and then create a write log on top of it. This write log is a purely log structured file system. So everything that we write in our entire file system is log structured. So log structured, be it a data that gets returned to SSD, be it a data returned to the slower media, the persistent tiers, all are log structured for us. And everything we write in this world is objects, and I'll tell you what that means. And when we look at SSDs, so let me use the board here. So when we look at the SSDs, so we divide on every node that is exposing SSDs. We create a logical what we call is a key space. One what we are calling it write log. The other one what we are calling is a read cache. So a given SSD becomes we use SSD for two constructs, for writing and reading. This becomes a write log, and in the write log we actually divvy up into two partitions, logical partitions again. What we have been calling is an active. Initially it starts with two active partition. So when the writes come in, I'll go to the mirror in a minute. Just for a minute, just ignore the mirror for a minute. When the write comes in, it gets returned to this active, so it gets appended here, right? As the write keeps coming, it gets appended. At some point in time, this will become full. The new writes will start going to this. This we will mark it as passive, and then we subject it to destaging. Okay, so it's a standard NVRAM. Think of this to be a ring of size of 2.
That's just a little bit simpler than making it purely circular.
And because of the mirroring, you have a similar layout for the mirrors also.
Exactly.
Right.
So now,
so a write comes in, it gets written to the currently active, it gets replicated to another node to its currently active, and then it gets act.
Yeah.
Exactly.
So
then that's all before data reduction?
It goes to the data optimization layer, which has the capability to both do the inline compression and the deduplication.
But so it's now I'm really concerned about the sequence, because deduplication adds latency, and I want that latency to be post-ACK latency, not pre-ACK latency.
Exactly, you got it. So because of the latency concerns,
so data comes in.
Yes.
It goes to the active half of the write buffer on the node into which it enters. It gets replicated to the active half of the write buffer in another node for protection.
Exactly.
Correct.
It gets ACT, and then it gets reduced.
Correct.
Okay.
Yeah.
So everything that we write,
Order matters.
Exactly, the order matters, because you nailed it. I mean, exactly for the latency reasons, we do not want to incur the overheads of the compression and the deduplication in the
pre-ACK. You want it post-ACK.
Yes.
Sorry, but I didn't understand. So you get the acknowledge when you get the copy.
I will go into that.
Go into the.
So I just want to give you a highlight on what a physical view inside a server, how we took SSD and how we consumed. We use as a two partition active, and there are 3 such partitions, right, total. One for mirror one, that is going to host somebody's first copy, another set for somebody's second copy. That's what we have. Now I'll go into how we do the mirroring, right? The write gets written when the write gets returned to the SSD in the primary partition there, in the active partition of a primary partition. Then we actually fork off to, let's say a file is configured for 3 copy, total of 3 copy, 1 primary and 2 mirrors. It gets forked off to write on the other one. When all of them are done is when we send the acknowledgement back to the client.
So key thing to note is all the 3 writes are going in parallel. They are not one after the other. It's not like primary is written and then the mirrors are sent or nothing like that.
What size are these writes?
Whatever the user writes are. The NFS request, you get like 4K or 8K or 64K.
Well, how is it breaking it up, the size of the write?
So we don't break it up. So as the RPC, so we get an RPC with, let's say, a whole bunch of 4Ks coming in. When our layer, at the top end of our stack, which is a write log code, looks at this thing, it pulls up all the, however many RPC requests come in, it puts all of them together, and it creates a local write of this. While it is creating the local write, it also forks off RPC into the remote nodes, and they also get executed concurrently.
But it doesn't. So NetApp would be doing this as a 4K write. vSAN would be doing this as a 1 meg write.
Oh, okay.
You know, that's what I'm saying.
Okay.
Like, how is
incoming
it
write? Okay, let's go into the details. Right, the NFS as a server, you would have published, this is my capability. I will do a maximum of 64K write. Right. Okay. Yeah. Then the client inside the ESX, if the guest has issued a 1 meg IO, he would have chopped into 64K IOs.
Okay.
As we get the 64K IO, we write as is. It is independent of the underlying file system block size. I mean, this is write log, right? Which is not subjected to the file system operations.
That's if we're going NFS. If this was going to be the SMB connection, does that stay the same? Change?
We might have to change for SMB.
Based on what is the write optimal write size.
So
request size.
We chose NFS the max transfer size is 64K. We can do 1 meg too if you want to.
I really don't care which way it is. I'm just curious as to which way you guys actually have it.
So 64K gives us the best bang for the buck without burning a whole lot of big buffers.
And the read cache, write cache distribution, is that fixed or is that something configurable? How much of a percentage?
Correct.
Yeah.
So because of this active and passive, as you mentioned, it's each of is a 2 gig of the write log, right? And you have for the mirrors. So essentially, you have taken 6 multiplied by 2, 12 gig. The remaining is given for the read cache.
So at max, a 6 gig of write cache per SSD. Is that what you're saying?
12 gig.
12 gig.
Yeah. 4 gig for the primary and the other 4 plus 4 for the mirrors.
And it's configurable. Right now, we've been using 2 gig and seems to be doing very good.
And then
It doesn't seem like it's enough.
Right? Doesn't seem so.
Depends on the back end speed.
Yeah, exactly. It depends on how you
How we flush the destage
the data.
You got it. Exactly.
Now, I have seen cases where one of the downsides to this kind of roll your own solution is people do silly things. And I've seen people have terabyte write caches that take days to drain. And
People do silly things regardless of
That's
the
one of the
platform.
reasons why we don't want to expose all this.
You got it. Actually, when you do that, it's painfully slow. All of them incoming IOs are going to tank. You got it exactly. That was actually internally. That's one of the heavily discussed topic as well. So
even more of a challenge,
we've been
'cause
able
when
to
they drain
flush
it is when the
extremely
data
fast
optimization
because
happens.
I'll talk to in the destaging
Compression.
how we flush the data coming from write log into the persistent tiers.
Which adds latency, but
we can do
reduces
striping
the load
within
on the back end
within
disks.
our the persistent
adds
tiers, so we
latency,
can
but
destage
reduces
very
the load
quickly.
on the back end disk,
So
so it balances.
I didn't get when you do the data optimization part. So after you've reached the from passive to active,
Yeah.
or before.
Okay.
Yeah. Very good. Very good.
Very good.
So.
As part of the destaging, he will go into the details.
That is the next slide. So you guys get it, right? So we get the write, we perform a transaction locally. As we perform a transaction locally, we parallelly we fork up mirrors. Once all the mirrors respond, is when we act back.
So these 2 mirrors, this is just taken an example, or it's a fixed case. For a data, it will be always 2 mirrors.
So you can configure this per object.
Okay.
Yeah.
So minimum 1 mirror or minimum.
So we recommend highly that customers use 3 copy because we want to protect against double disk failure. But I can definitely see a case where in the caching tier, SSDs, I've not seen the last 2.5 years in this company, I've not seen SSDs go bad. I've seen hard disks go bad. So it's okay for customers to configure caching tier with a 2 copy. But since SATA disk will take time for SATA disk to mature to enterprise classes, highly recommend them using 3 copies for hard disk tier. But there are going to be environments where customers are worried about how much usable capacity you get, because the 3 copy with the compression dedupe will get to 65%, 70%. If they want higher capacity, then the only way you can get that back is going to 2 copy.
Okay. 3 copy, you mean the actual data and 2 mirrors.
Exactly.
Okay.
Now, just to finalize on the part about if I were to issue a 2K write, will it write immediately? Does it buffer it with 62 more K of data?
No. No. I mean, the max size is 64K. If you get a 2K write, you will write to the SSD because that's the only outstanding write there.
Sure,
right
sure.
now.
And my follow-on question will go in when we go into data optimization of how we actually handle the dedupe and compression of that, but I'll wait till we get there.
Yeah. Okay. So another interesting point, I think you kind of touched upon the 2K, which is pretty interesting. One thing that we do pretty cleverly with the SSD, because we wrote our own log structure file system, we are very flashware level friendly. So for example, we look at the whole SSD as a collection of log segments, right? So all sequential. So we burn them out evenly, right? So that's one thing. The second thing is that when we write data, let's say you mentioned about 2K, let's say, but SSD page could be 4K or 8K. We always write at the SSD pages. Okay. Not only that, as we start writing the data and then at some point we destate the data, we do what we call as a reunit. We reunit the partition, which means that we release all those log segments that gets trimmed in the background, and then it is put back to the usable queue. So we are constantly we always write to a page that has always been trimmed. So which is something. So by doing so you're writing the SSD page size. You're always writing to a trimmed page. Now, the likelihood of FTL getting poked is very, very low.
But doesn't that mean you have to customize to the SSDs?
We don't need to customize anything. We are kind of varying.
You use the standard interface to trim the underlying blocks, right?
Right, but as the next generation of Flash comes out, page and block sizes vary.
Yeah. So we query exactly.
We query the underlying layer and then tune it to that values.
I'm just saying, when you read the device, when you first detect it, doesn't it tell you what it is?
No, not necessarily.
And if you have multiple generations,
because the SSD controller is making the flash look like a disk drive, and what you want to know is on the flash chips, how big is the page?
I agree.
Yeah.
So if the page today is 64K and tomorrow it's 128K, and you're saying we're doing everything in 64K because Micron makes chips with 64K pages, when the next generation of SSDs come out, you're writing half a page, not a page.
So this goes back to one of the points you made, and one of the challenges also, a lot of them don't expose this interfaces properly to query because they are lying. That's one thing that you mentioned.
Because SATA doesn't define how to do that.
Exactly. You nailed it. So in fact, we got an API, but we couldn't plumb through the right interface where it is generic enough yet. But that's where we will go. I think as they mature, they'll start exposing what the underlying block sizes and this is. Based on what we read on some of the SSD that we're going to use, that's the block size we picked.
Yeah.
Very good.
It's one of the advantages of NVMe. You can have that back channel.
To get the information.
Very good. So let me go into the destaging. I think this is something that you've been asking, right? So once we fill up the write log in the active partition, we subject them to what we call as a flash, which is the act of destaging. Act of destaging is taking that data that's been returned to an SSD and committing those to the persistent tier.
How large is a write log when you're destaging it? And is it based upon size or is it based upon time? I think of like consistency points and crap like that in the past.
Yeah, we'll go into the details of the consistency points when it's required for the snapshots and everything. But right now, the size of the write log, as Malik mentioned, it's like 2 gigabytes. But the act of the destaging can happen based on while the write log is full. I mean, when the active 2 gig is full or not. Also, there is a notion that because to address what all data has been sitting here, we are maintaining an in-memory tree to index the SSD blocks. So if the consumption of the memory for those indices goes to a certain limit, then we go ahead and start the destaging. So it is based on those two tunables.
So one good example for this would be, you wrote a lot of puny writes, like 1 byte writes. So you filled a 2 gigabyte worth of write log with lots of 1 byte writes. So now, before you even hit we set some memory limit for each one of these components in our system. Let's say that memory limit is hit first, then your destaging probably will happen even before you hit the 2 gig because the memory consumption has been hit. So these are the reasons why we'll do the active destaging. So as I was telling, the active destaging essentially around taking the data, and now you have to write to your data nodes and metadata v nodes, right? So let me introduce a little bit about the metadata v nodes and data v nodes. So what we have done, just like how we looked at SSDs and we create a cache v nodes, we take hard disk, and in hard disk we look at hard disk as or any slower media as a pool of log structured file system. It's basically collection of log segment in each one of them. So we group a collection of log segments and we call them v node, right? In the case of persistent world, this collection of v node, the collection of segments that becomes a v node can be either data v node or it could be a metadata v node. I will go into the details of what this helps us with. Okay, so when we destage the data from write log, we actually write to sets of data v node. It doesn't have to be a single data v node. It could be a collection of data v nodes on the same host, or it can even be at the remote one. So for example, you can have a situation where the system is in imbalanced state. You have an unused capacity sitting here and you want to leverage all that capacity. So now the active destaging grabs the data v nodes anywhere within the cluster, uses that for capacity, and then finishes the flushing and updates the metadata v node. We go even one step further. The same philosophy can exist in the when we look at the cache only server. Like let's say you have a node that has only SSD, right? It doesn't have any persistent tier at all. Now you have a transaction sitting in your write log that has to be destaged too. but your metadata data vnodes are not coming locally. They are really coming from elsewhere in the cluster. So we are able to flush the data, incoming data, not just locally. We can leverage capacity anywhere within the system. We are not only we're able to leverage capacity anywhere in the system, we even go to a mode where it can be only cache only server, and we are able to leverage the capacity within an entire cluster. And the next slide actually, and then when I write a data to the data vnode, we obviously, just like how we did for caching, we replicate the data across the servers for fault tolerance. So what this data vnodes, I think this is a very interesting philosophy about how do you really create a fine-grained notion of using your capacity, where you want to be able to go down to the level of 2 GB and be able to eke out 2 GB out of a disk, even if it is remote. So it's basically the bin packing problem, right? We don't want to be in bin packing issue, introducing bin packing issue. We want to be able to avoiding it. So the way we avoid is obviously first we try to uniformly distribute the data, but that doesn't guarantee, no matter how much you uniformly distribute, there could be imbalances. When we start seeing imbalances, our cluster resource manager, during the flushing, it starts giving you data vnodes from hosts or servers that are remote. So now you are able to grab that capacity and then to create evenness. Let's say you start filling lots and lots of data. If you have unused capacity in other parts of the system, like other servers, we are able to grab that capacity and start using that as well. So
is this balancing reactive, or is it based on the even hash distribution?
So initially it will start with what we call is a collocation. So we try to, if metadata is flushing to set up data, we try to give as much as possible local. If we start seeing an imbalance building in the system,
by that locality, do you mean locality to data that's logically okay?
Correct.
Got it.
So to particular pnode's write log you have written, you try to pick up the disks which are local to that pnode now. Okay, but the data vnode is coming from the different disk of that pnode.
Yeah.
If you see some imbalance, then you will start fetching the vnodes from
remote
the
servers.
remote nodes.
And then not only that, we are actually able to group a setup. We do striping at this level too. When we destate the data, now let's say you're writing your particular metadata and then you're writing all the data vnodes underneath that. We can grab any number of data vnodes, concurrently issue IOs to all of them. So effectively you are getting a striping, not just local striping. If you grab the data vnodes from remote, now you're able to perform transaction across the entire server.
So you're moving the data down to the data vnodes, so that's going to be the HDD tier.
Correct.
Yep.
When you've destaged it.
Exactly.
Is the metadata also going to HDD, or are you leaving that on flash?
No, we destage that, even that to the persistent
But
data.
for the metadata, what we do is we do a write through to the cache part of it, because you want the metadata to be accessed for the subsequent reads and writes also, right?
So
I'm sorry, let me try rephrasing my question just for clarity. The metadata, when you're writing it, are you writing it to the HDD or to the flash?
We do both. We do
okay.
both. Exactly. That's
where I got confused.
So essentially, we have a concept of when we write a data to the persistent tier, we do a metadata write through to the cache. So it will go into when I show you the cache, we have 2-level cache, and I'll show you the detail. It could be in memory or it could be in SSD.
And again, you're compressing the data and deduplicating the data as it goes from the SSD to the disk tier or persistent tier.
Yep. Yep.
And the metadata is maintaining that logical mapping for you to some extent, right?
Correct. So this is our core file system metadata, right? So there is a notion of a file tree. I mean, the way the different blocks are indexed. I mean, our file system block size is again configurable, can be like 4K, 8K. So essentially, you are writing in units of like 4K, which can be compressed and deduped.
Yeah.
Okay.
And 4K is the deduplication unit.
So it's actually it's a configurable as per the block size of the object. Basically, it could be 4K or it could be 8K, but it is fixed size.
Okay.
It is fixed size.
Now, can you in a 3-node cluster with a primary and 2 mirrors, can you experience a situation of imbalance? Wouldn't it be everything's either balanced or everything's imbalanced, because all transactions would be simultaneous in a way, performing across any node? Or or not? Is are you bogging down one particular node even though all the data exists everywhere at once? That's what the part.
So I mean that's a very good point. I mean, if you go up, right, you have the data access layer and data distribution. It might so happen that a particular part of a VMDK gets bounded, and some of the cache vnodes are going through a lot of the data in the write log, right? In that case, the corresponding, say, the file tree is getting flushed. Then there's a possibility that only the data for that file tree is getting destaged. So in that scenarios we can expect, but because you have so many files, when you have like hundreds of VMs, you have a large bin of inode, essentially UUIDs, which are mapping to a set of cache vnodes. We get almost a uniform distribution of the data.
Is the read cache data replicated or it's not? The write cache is, but the read
cache
is not replicated.
Yeah, we'll go into the details of how the read cache.
So the read cache could potentially be getting hit harder in one node than another.
Mm-hmm. Right.
So I'll go into the actually read cache. You're absolutely right, and there are some interesting aspects around when you hit the read cache with our dedupability, and I'll talk to it in the next slide.
It comes back to that dedupe level thing we talked about the other day, doesn't it? If one particular block is in hundreds of VMs compared to just, one block that's in 6 VMs,
then it can be Nova hot.
Yeah.
Yes.
And
cache?
Hopefully there's a RAM cache, so that Nova hot goes up into the RAM cache.
So the read cache is divided up into the two regions, which is a memory based and SSD based.
And then when that's not enough, you start making duplicates, which you guys aren't doing in code yet.
Is the read cache deduplicated and compressed?
It is deduped right now. I mean, we have disabled the compression because we don't want to incur the overhead of decompressing it in the read path.
So when the data is read from the disk tier and put into read cache, you decompress it.
Decompresses and
but
store
it's
it.
deduped.
Correct.
It's deduped, exactly. So
which also makes them all the same size and makes managing the cache a lot easier.
Actually, very interesting point.
Very interesting point.
Hang on to the point. I'll touch upon exactly.
We are very latency sensitive.
Yeah. So let me. That is by the way. That's your next slide. That I'll go right into it. So effectively, the way we can create data vnodes. It's a 2 gig worth right now. And it's a collection of log segment. It gives you a very fantastic ability to not only move smallest chunks of data from one disk and then start moving it to elsewhere. It also gives you another interesting ability faster rebuilds. So let's say a disk went out of state, right? Somebody pulled out and what have you, and then put it back. Now the data vnodes that are kept in that hard disk, now the sources for rebuilds can come from anywhere in the cluster. We can now do a faster rebuilds by fetching from multiple sources into the single disk. So that is another interesting one.
So it's a many-to-one rebuild, not a many-to-many rebuild?
It can be many-to-many.
Many-to-many as well.
I mean, he just took an example of pulling out one drive, but it can be many-to-one.
If you look at what the advantage of the 3-part compellent kind of architecture is that it does a many-to-many rebuild, not a
many-to-one.
So it is many-to-many, especially when a node, the example I give you is one disk pulled out. Let's say that when do all the disk in a node go down? One example is the whole node going down. That means all the drives could have lost some copies.
Right. But you're not doing the equivalent of RAID, where a disk in node X is mirrored to a disk in node Y, like vSAN does. So when that disk fails, there's 4 terabytes of data to do a one-to-one replication.
You nailed it. Essentially, you created 2 logical space, both in the SSD and the disk one, and this 2 gig entity gives you not only sync and rebuilds and fasters, but when you write to them, I mean, because of the striping nature, you are leveraging all the physical resources in a concurrent way also.
And also there are some other, because of log structured nature of this, the vnodes for us, also allows us to quickly discover what has been missed when the node or a disk goes out of state, because we look at the top of the segment identifier, look at what the gaps are, we sequentially copy all the data. And the beauty is that you don't need to, just like whatever, you don't need to rebuild the whole disk. You're rebuilding only for data vnode that miss those updates. That's right.
So can you control that? Can you throttle it? Can you prioritize it in any way?
Yeah, so we have a way by which our cluster system manager, when it detects a node going out or a disk going out, it schedules a sets of what we call as a parallel resyncs, parallel rebuilds, and it periodically schedules if there's a lot of IO coming in and then hurting the flash time. you will start throttling a little bit. But in general, having said that, we strive for restoring the health of the system with a more important element than the performance, if I may add. So,
well, it depends how you look at it, doesn't it, really?
Yeah.
Depends on what you're trying to rebuild. If you had one or two VMs that were much more important, you might want to get those rebuilt first, and you might not care if the others aren't rebuilt.
And it depends if I suffered a 1 of 2 copy failure or a 1 of 3 copy failure.
That is,
because if I've suffered a 1 of 2 copy failure, protection is more important than performance.
When you're in a single copy one, we don't know which VM, how important that is.
No, but that could be a policy, couldn't it, that you could apply?
That is true.
Yes. I mean, we are planning to integrate with the so-called the storage policy-based management, so that we can tag a particular policies like availability, highest factor, then rebuilds take priority over the rest of them.
Especially with vVols, then you've got the policy applied to the vVol.
Good.
If I could briefly revisit one of Howard's points earlier, assuming, say we've got 5 nodes in there, 2 of them are first gen, 2 of them are second gen, and we've just added a third that's third gen, how well will they interoperate and work with each other while they're all within the same CPU? No, they're not in the same CPU families, I mean, to be honest, right?
The question is, do you balance evenly, or do you balance as an even percentage of capability?
We try to look at only the capacity and then try to rebalance.
The good news is you only have first generation customers, so you got like 2 or 3 years before you have to worry about it. But ultimately, you want to be saying we're going to balance this evenly as a percentage of the node's capability.
Well, I mean, you say first generation customers, but if people are saying, I can throw this onto my old stuff, a la the original VMware story, hey, I'm going to repurpose this and build my, build my own rig at home. Truly, because you'll end up with a whole bunch of...
Enrico wants to run on 3
You say you can use any commodity hardware from Phil and Blake of random vendors.
Correct.
They just might do that. And that's why I want to make sure where we stand from that standpoint.
Right now it is uniform. We don't have a notion of a P-node capabilities with respect to CPU memory and all that, but those are the other parameters which we can add in the subsequent versions. So one thing to note is when we write to the log segment, every unit of block which is written is checksummed. And the way we write is optimized based on the medium. Like the flash, the kind of we pack the segments is different from the way we pack the on the spinning medium.
Okay, so you're writing checksums for data integrity?
Correct.
Where are the checksums written?
The way they are stored are like as part of the segment itself. There is what is a notion of an IO header for each of the block which is written. The IO header has a checksum.
And that block is how big?
The file system block, like
4K.
The 4K, 8K.
4K or 8K, depending upon what the the object.
That could be problematical. Because the new 4K SATA drives, you're writing one sector, and about 1 in every 10 to the 17th writes actually gets written to a different location than you told it to go to. And by storing them together, it's not as good.
I'll explain this. Very good point.
Very good
so when the act of destaging, the act of destaging, when we flush the data, we don't write the 4K immediately to the hard disk. What we do is that we do what we call as a packing. So when a flusher destages a whole bunch of data for that particular inode, all that gets first packed in memory, and then we write a one gigantic write, 1 meg write or 2 meg writes. That's how we do it. So we don't write even though in the data, that user data you wrote is 4Ks, a whole bunch of 4Ks, they all get packed in one segment.
Okay, so view it as
I understand. It will take a long time. We'll take it offline.
Okay, we'll go into all the details.
Definitely, yeah.
The key point is the checksum is in the software. We do not rely on any hardware checksums.
Right. No, and better to have than not to have, and we'll deal on the details of exactly how it goes offline, because it's deep and will eat up a lot of time that
No problem.
Sure.
thee and me will get, and everybody else will be bored out of their brains.
Now let me walk through the read cache. I think you had some questions around it. So imagine that now the VM did a VM or a container, whatever it is, and did a read on a particular stripe that landed on one of the cache node. The first thing we do is obviously IO comes in. We first look to see if the data is in write log, right? If there is a write log, we return the data from the write log, which is sent, backed by SSD. If the data is not there in the write log, then the first thing is we do a lookup on memory, right? If the object exists in memory. And I'll tell you, we'll walk through a scenario where it's a miss across, and then we'll talk about hits. Let's say it's a miss on L1, then we go look at L2, which is backed by SSD. Let's say there's a miss on SSD, then we'll go to the persistent tier, fetch the data, right? Let's say this metadata was already in memory, let's say only the miss was in data. As we fetch the data from the disk, we already have a fingerprint for this. So we only store the fingerprint and the data in SSD and DRAM, right? So we store in both places. Obviously, the memory that is given to us for a caching is very puny, right? It's configurable. The SSD, on the other hand, is pretty big, so you can host lots and lots of data. So we store in both so that you can evict from memory, but you can still keep it in the L2, which is our SSD. So as we store the data, as I was telling, fingerprint and the value. What this allows is fundamentally now dedupe lots and lots of data. If you have two different files whose contents are identical, the inodes may be different. In the traditional caching system, you would have two copies of, because you track in the cache inode and offset, right? What we track is, we don't track inode and offset, we track fingerprint and content, because our entire file system metadata is based on fingerprints, right? Because we do dedupe. So we built our entire file system metadata in fingerprints. If two inodes or two objects point to the same fingerprint, we'll be able to leverage the data that is, fetched by someone else if the fingerprint matches.
Especially in a VDI kind of use case, especially when you have like Bootstorm, Login Storm, it's a huge win, because one IO can serve like thousands of VMs IOs.
Yeah. Okay, so likewise, I only show one node. Because of the way we are striping, you can actually read parallelly from across the entire cluster. And then let me talk through the data optimization. I think we briefly touched upon when we destage the data, we chunk them into fixed size, which is the size of the chunk is based on the block size of the object. So it could be 4K or 8K or 64K, whatever you choose it. And then we chunk them, and then we produce a fingerprint, and we do a lookup. The one difference that we have done versus traditional way of doing this, we don't try to index all the data in a system. What we've done is that because we don't have a lot of memory, we have puny amount of memory and it's configurable. We use an algorithm called majority K algorithm, which is based on similar to a Zipfian distribution. You have 90% of hit is to a 10% of data, 10% of hit is to a long tail of 90%. So we follow a very similar algorithm. We study the fingerprints that have a very high probability of getting deduped to. We only store those. Not only that, there is some amount of memory given to it. We can only pack that many of the K elements into the memory. So we do inline dedupe that way very efficiently, and we don't dedupe against everybody.
So you effectively cache the hashes as well as
sorry?
You are caching the hashes as well as the data.
Yeah, correct.
Based on hash frequency of access.
Yep. You got it. That's pretty much one way to look at it. So frequency with what they call Zipfian distribution, right? Where are the hits coming to? You try to only optimize for those cases as opposed to trying to keep index for everybody.
It's on a per cache vnode basis. Is that so? What's get hit in one vnode may not be what's getting hit in another vnode. Cache vnode?
Currently that's the form, but we are thinking of a way of aggregating a set of cache vnode to a particular file tree so that you get deduplication across the multiple file system trees also.
And you're deduping in 4K chunks, or you're doing it in variable length based upon what the...
It is definitely fixed, but the size of that chunk is based on the underlying block size of an object. Right? If you have two VMDK, one you could have configured for 4K, other it could have been 8K. The dedupe size is either 4K or 8K.
You're expecting if a data object is replicated, it's going to have the same block size.
Correct.
Roughly. Yes.
Yeah.
And the other aspect is, talked about compression. Everything we write, because we're a log structured file system, homegrown log structured file system, everything we ever write to a log structured file system is always compressed and appended and kept moving.
So from write to ACK is really fast.
Correct.
Yeah. From ACK to commit to disk with deduplication and compression.
Correct.
Is that just as fast, or I imagine it's a little slower, but like how much slower is that?
So it is completely a throughput-based system. That's where like stuff that I was talking about using data V nodes and striping across data V nodes. The faster you can leverage hard disk, because you have lots of disks. Your goal is to flush data by leveraging all the spindles, right? You can read at a 400 megabytes a second from SSD, or 450 or 500 megabytes. In fact, we have an in-memory copy of the write log itself. Read from memory, you have to try to use as much as possible all the spindles by sprinkling across all the data V nodes, so you can create a flush, finish the flush extremely fast.
It's technically incorrect to say you're doing inline data deduplication or compression, because the data is written uncompressed and undeduplicated.
Correct.
And in fact, when you read it back and you're caching it, it gets uncompressed during that stage.
Capacity tier and the read cache tier is completely deduplicated, and the write log portion of it is not.
The cache tier is not deduplicated if it's being written. You said it was not deduplicated at write. It's only deduplicated when it's destaged.
No.
I'm talking about the read cache part of it.
So this one, as we fetch the data, I was telling.
But when you say it's inline deduplicated, inline compressed, the implication is before an acknowledgement is done, it's decompressed, it's compressed and deduplicated. And the answer is that's not the case.
You might be strictly speaking right, but the vast majority of systems that say they do inline, they do it post-ACK.
Well, you don't
it's
want to
before
wait
it.
for the
It's before it writes.
Just mirror, acknowledge.
SolidFire
then
does, Pure
optimize.
does.
Yeah.
I mean,
I think I prefer it that way.
Right, because you're not delaying the
it's
acknowledgement.
I'll give you that you're semantically correct. I'll also say I would prefer that it not.
I understand the preference.
Okay.
I understand the preference.
Can you clarify the third bullet?
Striping enables deduplicate.
The third bullet.
Oh, the inline compression on SSD and SSD.
There's a missing word in that sentence, or there's an additional word.
There's a missing
on
hyphen
and.
as well, isn't there?
I was sleeping. Sorry.
No, that's fine. Can you tell us what it should have said?
Inline compression on SSD and HDD.
Okay.
Yeah. Sorry.
So, but you're not compressing in memory. Deduping in memory.
Correct.
And compressing everywhere. Okay.
To save the
only compressing.
decompression cycles
cycles.
on repeated reads.
Yeah.
Correct. And obviously this goes on every node. Sorry, you had some question?
Yeah, and I got what I need.
So if it were like VAI supported, so if you were to write a bunch of zeros, okay.
Oh, so zeros is a very special case.
Yeah.
We don't write any zeros at all.
I wouldn't want you to, but
Zero is a special deduped entity in our system, because we don't even write the data for it, even for the first zero itself.
Yeah.
Or if you're writing Fs,
Yes. Yeah, then it gets deduped.
So
and even if there is a valid data, and if you overwrite with the zeros, we reclaim the space for that also.
Sure.
There's a really intelligent space reclamation policies there too.
Because 5 years ago, zeros were a problem.
We have a time crunch on the section. So.
Damn.
This is one of the jewel of our technology. If I can just talk for a couple of minutes, or
It's your time. I think we should manage. We should give some time to the demo. So maybe.
Okay. Okay. I'll. Okay. Here's what I'll do. We'll end right at 5:15. Then at least. Unless you guys. Okay. So we support native snapshot and cloning capabilities. Obviously, for us, clone is a writable snapshot. Essentially, we are pointer-based snapshot. I'm sure you guys hear this. But our transactions, when you take a snapshot, is extremely fast in the sense that we only log a simple transaction. This inode is derived from this base inode, and that's it. That's the only transaction we commit to the SSD until we destage the data. Even when we destage the data, there is not much of update at all. It's like a simple metadata update for the new inode that got created for snapshot. Extremely fast. And therefore we can do a fast creation, fast deletions, and no consolidation or compaction overheads, right? And we can do this at a fine-grained level, at a VM level. We can also do at a folder level, say a group of VMs, or at the resource pool the VMware has. We can do at that granular.
Oh, so it's at any level within the folder tree?
Yes.
So by defining the folder tree, I essentially create consistency groups.
Yeah, and well, it doesn't quite give you the whole consistency across this because they have to quiesce each one of the VMs, right?
Right. But there's always the simultaneous quiesce problem.
Exactly.
It is not the whole group consistency, but the quiesce points of the individual VMs and the native snapshot of the individual VMs.
That's what we get.
Okay. So you're all set up for Vival.
Correct.
Yes.
Yeah. And then we have, and I think someone asked me that we support VAI. So we do native snapshot and cloning for the ESX side, and for the OpenStack environment, we have a Cinder. We started working with the Docker workgroup. We just started about 2 weeks ago with the Docker. The workgroup just started, so it'll take some time. And then the beauty of one thing is that because one of the mantra I was telling you, we want to empower server admin, which means the management console has to be as much as possible something that he is used to. So we did not go develop our own snapshot manager. We actually did all the snapshot management, everything. And you can actually manage through the vCenter's snapshot manager, so that admin doesn't have to learn yet another management tool, right? And it's a policy based. You can do schedules, retention policies, nightly, weekly, and the whole 9 yards around it. Okay, and then this is what I was saying, and I think we can do the demo of this, and you'll get the video. So we did not develop our own management pane. We have Bootstrap. Once you do a Bootstrap, that's it. You go to the vCenter management pane, and likewise we will do for SCVMM and as well as for Horizon. Of course, in the OpenStack, a lot of people will go towards the REST-based API, so it will be more skewed toward automation. You will appreciate when you look at this look and feel of this will look a lot closer to what administrator used to. We did not go and make his life complicated. We have created a lot of shortcuts going between the DRS cluster and Springpath cluster and whatnot. So we'll see that in demo. But the philosophy is that we don't have any separate management GUI. We do provide, there is a vSphere web client for things that is not captured, and we don't want to be replicating any functionality that's already been provided. We don't want him to be learning. So we only given primitives such as what is my health of the disk, and what's going on with the entire cluster. Is a 4-node available or 3-node available, 2-node online average, is in a degraded mode. Some of the performance metric that wasn't quite captured in vSphere side also we give a visibility to it. And this is my last slide. So in summary, I think we have created a homegrown log structured layout, and the main reasons are we want to provide flash endurance, compression friendly, and the faster rebuilds time. We are able to do data virtualization, and therefore customer gets a benefit of being able to scale performance capacity tiers independently. We are able to do data distribution to achieve fine granular scaling and rebalancing and uniform distribution in the entire cluster. We are able to build a fantastic data services, therefore the customer are able to get fast snapshot and cloning capabilities. And we make our management of our cluster dead simple by offering an integrated management solution to the customers. Cool.
So just one quick question. I assume because you're virtualizing every piece of the physical disk and infrastructure,
yes,
it should be very easy to evaluate your software in a virtual environment.
Yes.
And just spin up virtual machines. Virtual machines.
Yeah. It's actually you can even run it in. I mean, even without tying it to hypervised environment, you can even run it in a Docker container. You can create file as a disk. Obviously, as a company, we can't give 4 servers or 5 servers every single user. So internally, we have actually built a mechanism that allows you expose file as a disk to our controller software. So actually, you can create like 3 files, using device mapper.
Yeah.
And then, so that's how we've been internally doing a lot of testing.
I was just thinking of just nested ESX, for instance.
Nested ESX
is also a possibility too.
Yeah. Even the easiest one, I'll tell you, pick a 3 Docker container, run our software with the files backing that. Boom.
Send us the software, we'll have it done.
Yeah, the power of software.